All right, everyone, this is the question that we left you with yesterday for homework. We have a 47 kilogram object. It's being pulled in one direction by 100 newtons. It's pulled in another direction by 30 newtons. And it's pulled in another direction by 50 newtons. I think we made it a bag of candy, right? And I can't remember who the people were that were pulling it. It's just 100 newtons, 30 newtons, 50 newtons. It doesn't matter, right? Okay, we call it F, whoever it was that was pulling it, F T for force of Tyler, whatever, it doesn't matter. Call it F1 or F2 or F3. The names of them are really irrelevant. Okay, we want to find the net force and ultimately the acceleration. But the problem is we've got two funny angles, and we don't like funny angles. So the first thing we got to do here is get rid of those funny angles. Okay, the first one that I'm going to get rid of here is the 30 degrees. Oops, wrong way. Let's go in a different color here just to differentiate here. We've got 30 degrees right here, and we've got a hypotenuse there of 50 newtons, I should say. This is x, this is y. We're going to say cosine 30 degrees is equal to adjacent over hypotenuse, or x, the adjacent side, is going to be equal to 50 times cosine 30. And that's going to work out to be, I believe, 43.3. Is that right? 43.3 newtons. Now we're going to do the same thing for the y component, except with the sine function. Sine 30 degrees is equal to opposite over hypotenuse, and y is going to therefore be equal to 25 newtons. How many people have this so far? Okay, good. Now let's do the other one now. Let's do the 30 Newton vector at 60 degrees. Okay, here's our angle at 60 degrees. Okay, this is x, this is y, this is 30 newtons. We're going to say cosine 60 degrees is equal to x, the adjacent side, over the hypotenuse, 30. So x is going to be equal to 15 newtons here. We're going to say sine 60 degrees is equal to y over 30 newtons. And y is going to therefore be equal to, I think it's 25.5 something? 25.98? 25.98 newtons. All right, so what I can do at this point, if I want, is to replace this 50 Newton vector with a vector that's 43.3 newtons and a vector that's 25 newtons down. I can replace this 30 Newton vector with a vector that is 15 newtons to the left, and with a vector that is 25.98 newtons upwards. Well, now I don't have any funny angles, but I still have vectors that are in more than one plane. If it was all this way or all this way, then I could just say F net is equal to the sum of the forces. But since there's sum on both axes, I've got to do F net is equal to the sum of the forces twice. F net is equal to F1 plus F2 plus F3. How many people have the right answer so far? Okay. The net force is also m times a. The mass is 47 kilograms. The acceleration is what we're looking for. F1 is going to be 100. 100 to the right. F2 is going to be what? I honestly don't remember which one was next. Is it 15 or 43? Does it really matter? No, as long as we use them both eventually. Negative 15, because it's to the left, and then we've got negative 43.3, because it's to the left as well. So we're going to say here 100 subtract 15 subtract 43 divided by 47. How does that give me? 0.88. Okay, thank you. 0.88 meters per second squared. Now that's not my acceleration. That's the x component of my acceleration. Let's do the same thing for the y component and see what we get for that. Let's say y F net is equal to the sum of the forces again. Let's say mass is 47 times A. What's F1? Quick. 0. because it's all to the right, and we're looking at the y-axis here, right? That's the x-axis, that's the y-axis. So it's going to be 0. F2 is going to be 25.98. And F3 is negative 25 newtons. So that's going to be 47 times A is equal to 0.98. And that's going to be a pretty small acceleration, right? What's 0.98 divided by 47? About 0.02? Keep going, though. Let's go a few more decimal places. 0.02. Or is that exact? Okay, good enough. That's our y component of the acceleration. Now all we have to do is combine them. 0.88 to the right, doesn't matter that it's acceleration vectors. Could be velocity, could be displacement, could be force. 0.020 meters per second squared upward. The resultant vector that goes from start to finish is right there. Now let's solve for A. It's the square root of 0.88 squared plus 0.02 squared. What do we get there? How did you have that one? And the angle would be the inverse tan of opposite over adjacent. 0.02 over 0.88, which is going to be a pretty small number, right? What is that? 1.3 degrees, and it would be north of east. 1.3 degrees north of east. Good? How many people got that? Good. Good. Let's have ourselves a little quiz on this tomorrow. Okay? So, no tricks to it. Okay? It'll essentially be this problem. Different numbers, maybe different directions, but no harder, no easier than this question. Happy? Good? All right. Today we're going to go into the next section of the unit, which we typically put along with dynamics, although this time we're having our little test on Tuesday on forces, separating this. So we'll call this a new unit, I guess. It's on energy. Some of the stuff that you did with forces wasn't new. Some of the stuff you did with forces you would have taken a look at for the first time in Science 10, although not nearly in the detail to which we covered forces. Energy, you've probably covered most of this stuff in Science 10. Maybe not quite the detail, okay, but it should really ring a bell from Science 10 if you think back to grade 10. Let's define energy first of all. Energy is one of those things, kind of like time. Okay, everybody knows what it is, but nobody can really define it very well. Okay, time is what? I don't know. I can't think of a good definition for time. I can't define it very well either. Okay, energy is kind of like that, except energy is a little bit easier to define than time. Okay, we all know what it is, but it is a hard one to actually define. We define energy, now technically, scientifically, we define energy as the ability to do work. So energy is that mysterious quantity that can make this pen fall to the ground. It's that mysterious quantity that a car has as it's traveling down the road. It's the mysterious quantity that is either doing something right now, the car traveling down the road, or has the potential to do something later on, like the pen as it sits up here in my hand, ready to fall to the ground. There are two kinds of energy, and I kind of just alluded to them just a second ago. Does anybody remember what they are from Science 10? Think harder. You all have the potential to recognize at least one of these types of energy that you saw in Science 10. Every single one of you has the potential to see that. Okay. What's one of them? Dustin? Hey, potential energy, good. Potential energy is one of the two types of energy. What's the other kind? Kinetic energy. Now, what's the difference between kinetic and potential energy? Whoops, don't want to give you the answers here. What's the difference between kinetic and potential energy? Yep. Good. So kinetic is when it's doing something now, right? We said energy is the ability to do work. Kinetic energy is doing work now. Potential energy is what? Austin, what's potential energy? Okay, yeah, I mean, you're defining a term in terms of itself, but it pretty much says it, right? It has the potential to do something. It's stored. Okay, you can do something down the road. It has the ability to do work. It just isn't doing it right now. Kinetic energy, the energy of motion. Moving objects have kinetic energy. Potential energy is stored energy, energy that's not doing anything right now, but can do something under the right circumstances. Give me an example of kinetic energy. A ball moving? Sure. I have kinetic energy right now. Okay, I'm moving. The Earth has kinetic energy as it orbits around the sun. The air has kinetic energy outside because it's blowing a little bit, the wind. But the air molecules themselves have kinetic energy as well because there's thermal energy stored in them, and thermal energy is the vibration, right? That's kinetic energy. Anything that's moving is kinetic energy. We can express kinetic energy as a number. The equation that describes kinetic energy is not a new one to you. EK is equal to 1/2 mv squared. Remember that? I heard the sigh, oh my goodness, oh my goodness. What does that mean? Is that not a good thing, this equation? Okay. So this is kinetic energy right here. Does anyone remember the units for kinetic energy? Somebody just said it. Somebody just whispered it. Say it out loud. Joules. Joules. What's M stand for? I can virtually guarantee you you're going to get one of these wrong. Who wants to go out on a limb here and say they think they know what M stands for? Think you know? Be courageous. Get off that fence. Tell me what M stands for. You guys know this? M stands for? Tyler, what does M stand for? Yes. Good. Tyler, I let you off the hook because I gave you the easy one. Units are kilograms. Bet you all wish you were Tyler now. Somebody's going to get called on for the hard one now. What does V stand for? What does V stand for? Let's see who we can pick on right now. Oh, Luis has got his hand up. That means he knows this, right? Luis, what is it? What did I expect somebody to say? Not volume. Velocity. Velocity. It's not velocity, it's speed because there's no vector sign over it, right? We don't want the direction in here. Okay, if it's 28 meters per second to the west, I don't care. It's 28 meters per second. Okay, we want speed here. And we want it measured in meters per second. So the kinetic energy of an object that's moving, doesn't matter whether it's a molecule that's moving in the air outside or whether it's the semi-truck that's traveling down the highway, Highway 2, kinetic energy is described by 1/2 mv squared. Now, potential energy is a little bit harder. Stored energy is a little bit harder because there's lots of different kinds of stored energy. Energy that's not doing anything right now, but has the ability to do something down the road. Can somebody give me an example of a type of stored energy when an object has potential energy or stored energy? I gave you one already. Good, good. What kind of energy is stored in your muscles? Sorry? It's stored for motion, yeah. But what kind of energy is it that's stored there? Potential, right? But specifically, it would be chemical potential energy. A chemical potential energy is stored in your body, okay, it can get harnessed and be converted to kinetic energy to make you walk or run or jump or talk. Chemical potential also exists in gasoline. Okay, gasoline, you fill up your car, it's not doing a thing. But there's this 60 liters of gasoline that's stored in your gas tank, which has the potential to make you move. Chemical potential energy. It's the same energy that's stored in a chocolate bar. Okay, my son played hockey this year, 11 years old, played atom hockey. I don't know what it was, but there was about half the team, they insisted on having a chocolate bar before every game. Okay. They thought they were going to get this big boost of energy. Well, they might for 5 minutes or so. And then after that, they had that little sugar crash. In the end, there is energy stored in a chocolate bar, right? And it's in the form of chemical potential energy. So it's all essentially the same thing. What's another kind of potential energy, though? That's not stored in chemical bonds, basically. Yep. Mechanical energy is actually, it's not potential. Mechanical energy is the sum of kinetic energy plus potential energy. So it's really both of these combined. Okay, so it is a kind of energy. You're not coming up with a word that doesn't mean anything. It's just not a type of one of these kinds. Rather, these kinds are a type of it. Okay? Yep. Gravitational potential energy is another good one. You guys all, as you sit in your desks right now, have gravitational potential energy relative to the floor. If I all of a sudden pulled the desk out from underneath you, what would happen to you? You would fall to the floor. So you have energy stored in you relative to the floor. You could fall to the floor at any moment if the desk disappeared. If the ghost in the room just mysteriously took away your desk, you'd fall to the floor. Stored energy, it's not doing anything right now, but has the ability to do work. What's another kind? Chemical, gravitational. What else has stored energy? Another type of potential energy, elastic potential energy. The energy stored in a stretched elastic. When you stretch an elastic, okay, you pull back an elastic and let it go, fling it, okay, it starts moving. Well, if it's got kinetic energy, if it's moving across the room, flinging towards somebody, then it must have had potential at some point. Okay, the potential energy, you can't get kinetic when you don't have potential. Potential, stored energy, always comes first. It's what's converted into kinetic energy. Elastic potential energy, due to an elastic that's stretched. Another kind that kind of goes with elastic is spring potential energy. When you stretch a spring or when you compress a spring, it's got potential energy. Remember when I was a kid, I had this little ping pong table, not a ping pong table, but a pinball table. And it wasn't a good one like you see in a store or whatever. It's just this cheap thing that came from a Walmart type store. But I used to play with that all the time when I was this little kid. And I remember this stainless steel ball would hit the spring and then it would bounce off. It would spring off at a pretty good clip. Well, it was stopped momentarily, right? The little pinball would be moving, and then it would hit this spring, and then it would stop. So it's not moving, but then it is moving. So we had an object that wasn't moving at all of a sudden, a fraction of a second later, was moving. It was something at rest that now has kinetic energy. Well, the kinetic energy had to come from somewhere. It came from the spring potential energy, the energy stored in the compressed spring. Okay, it also exists in stretched springs as well. Now we're getting a little bit more abstract here. Even something like nuclear. Okay, that would be the energy stored in the nucleus of an atom. Okay, sometimes in a nuclear power plant, we don't have any in Alberta, but I grew up in Nova Scotia, and there was a nuclear power plant in a place called Point Lepreau, New Brunswick, which was different province, and to drive there would take a good probably 3 hours, 2-3 hours to get there from where I lived. But this is New Brunswick right here. Okay, this is Nova Scotia right here. Okay, right across this right across this Bay of Fundy here, which you could actually see New Brunswick from Nova Scotia across this Bay of Fundy, okay, was this place called Point Lepreau, where this nuclear power plant. Okay. It generates electricity. Okay, well, where do you get the energy from? Where do you get electrical energy from that can ultimately be converted into motion, kinetic energy? Okay, it comes from the energy that's stored in the nucleus of an atom, nuclear energy. Any other kinds you can think of? I just kind of gave one away if you guys were listening. How about electrical energy? Electrical potential energy. That can cause motion, right? Electrical potential energy can certainly cause motion. All kinds of potential energy. There's two types of potential energy that we're going to focus on. Gravitational potential energy and elastic and spring potential energy. We'll focus on those in time. Right now, I want to pay pretty close attention to kinetic energy. We'll master that, and then we'll deal with these two kinds of potential energy, gravitational and elastic or spring potential. 6.5 is based on kinetic energy. Notice we're on chapter 6 now, so if you don't have chapter 6 downloaded, you should probably do that tonight. It says on a highway, a car of mass 1,200 kilograms is traveling at 20 meters per second, has a kinetic energy equal to a loaded van of mass 4.8 times 10 to the 3 kilograms. What's the speed of the van? This is actually a pretty hard question to start off with for kinetic energy. It is. We have two cars here, two objects, a car and a van, both with different masses. Which one are we trying to find the kinetic energy of? They both have kinetic energy. They're both moving. Which one are we dealing with? Both. We're told here that the kinetic energy of the car is equal to the kinetic energy of the loaded van. So let's say EK for car is equal to EK for the van. Now we know the equation for kinetic energy, it's 1/2 mv squared. So let's say 1/2 the mass of the car times the speed of the car squared is equal to 1/2 times the mass of the van times the speed of the van squared. So if we're just looking for kinetic energy, just say EK is equal to 1/2 mv squared. But if they tell you two kinetic energies are the same, then let's set them equal to each other. Now, I don't know if anybody sees this or not, but you can actually make a little mathematical shortcut here. Did anybody spot what I'm thinking about here? Yeah, if one variable appears in both terms, you can get rid of it. The half cancels there. You don't have to cancel it. You don't have to cancel it. You don't have to cancel the half. But you can. It just makes life a little bit easier when you go to plug it into your calculator. The mass of the car, 1,200 kilograms. V is 20 meters per second squared, is equal to the mass of the van. It's 4.8 times 10 to the 3, or 4,800, times the speed of the van squared. Well, 20 squared is 400. 400 times 1,200 is 48. 480,000 joules. That's equal to not joules, but 480,000 equals 4,800 times v squared. 48,000 divided by 4,800 would be 100, I think. Somebody check that. We're going to square root that now, and we're going to get v is equal to 10 meters per second. So a car has 1,200 kilograms and 20 meters per second. The van has a mass that's quite a bit more. The speed is quite a bit less. Would you expect that? If it has the same kinetic energy, and kinetic energy is based on mass and speed, well then when mass goes up, speed is going to go down. Take a look at the numbers there though. The mass quadrupled. Why did the speed not go down by a factor of 4? Because it's squared. Because it's squared. 10 meters per second is the speed of this van. Does that make sense? It's kind of a hard question, like I said, to start off with for kinetic energy. Okay? You guys can handle that now, though. You guys are smart now, right? I was a lot smarter than you were 2.5 months ago when you started this class. All right, let's try these 3 questions, please, on page 303. Let's see what we can do with those. One quick little thing, guys. One quick little thing. We don't want kilometers per hour, do we? You guys remember how to convert kilometers per hour to meters per second? It's been a while since we've done that, actually. Kilometers to meters, multiply by 1,000. Hours to seconds, 3,600. So it becomes multiply by 1,000 divided by 3,600 to get meters per second. Meters per second will always be a smaller number than kilometers per hour, so that can be your little check. Okay? Now let's see what we can do now with these 3 questions, please. All right, guys, if we're not having too much trouble with those questions, let's take a look at one of the types of potential energy that we said we were going to discuss in a little bit more detail. Gravitational potential energy. The energy stored in an object due to its height. It's always measured relative to something else, usually relative to the ground, although not always. The more the height above that reference point, then the more the gravitational potential energy. I got a pen in my hand right now. What's the gravitational potential energy of this pen relative to the ground? Well, you don't know a number for it, right? But you do know that if I drop it, it has potential to fall to the ground. Agree? So it has potential energy relative to the ground. What about relative to my hand? Does it have potential to fall to my hand? No, it's already in my hand, right? Do you have gravitational potential energy relative to the floor? If I take away the desk, will you fall to the floor? Yes. Do you have gravitational potential energy relative to the desk? Will you fall to the desk? No, you're already in it. Right? A couple summers ago, I went cliff jumping in a place called Maple Lake in BC. Seems to me the height of the cliff was something like 10 or 15 meters, which doesn't sound like very, very high, but let me tell you, when you're standing up at the top, it looks really high. The gravitational potential energy that I had that day as I was jumping off of this cliff was 0 relative to the top of the cliff. Right? I had no potential whatsoever to fall to the top of the cliff, because I was already there. Right? I could walk around, couldn't walk around very much because it was a pretty narrow ledge, but you know what I mean. Like you have no potential to fall there. But you do have potential to fall to the water. So there was potential energy relative to the water, relative to the lake. So potential energy, the energy stored due to the height, relative to something else. Now let's come up with an equation for potential energy. EP, instead of EK, EP, is equal to, what do you think it's dependent upon? What has more potential energy? This pen at the top of the cliff or me at the top of the cliff? Which has more potential to fall? Which has more potential? Here's the way you got to put it. Okay? Which has more potential to cause a big wave when you hit the water? The pen when I drop it, or me when I drop myself? Me, right? If I had more kinetic energy when I hit the water, then I must have had more potential energy when I was at the top of that cliff. So what's one of the factors that affect potential energy? Mass, good. EP is equal to m, mass, times something. I showed you guys a video way back in February when we were talking about acceleration due to gravity. I showed you a video of an astronaut on the moon dropping a feather and a hammer at the same time. They both fell at the same rate. But we also noticed that both of them fell slower than they would have fallen on Earth, at least than the hammer would have fallen on Earth. In other words, if you drop a hammer on the moon, it will have less kinetic energy when it hits than it would on the Earth. Right? Why? The acceleration due to gravity. So potential energy is going to be related to the acceleration due to gravity as well, g, which for us is almost always 9.81. And on the moon it would be 1.6. On Earth it's almost always 9.81. What else? You drop that pen into the water, from the top of the cliff, or I throw myself off of the cliff into the water, what's going to create a bigger wave or a bigger splash? When I go off the first ledge that's 10 meters off the 10 meters away from the water, or that second ledge that's 15 meters away from the water? What creates the bigger splash? Or the height, right? Yeah, yeah. So if I have more kinetic energy when I hit the water, if I jumped off of the 15-meter high cliff than the 10-meter high cliff, then I must add more potential energy to give me that kinetic energy. So the other thing that affects gravitational potential energy is the height. EP, we're going to say is the gravitational potential energy, and the units for that are going to be joules, just the same as they are for kinetic energy. M is the mass, and that's going to be in kilograms. G is going to be, most of the time, 9.81 meters per second squared, although it could change depending upon where you are. Usually 9.81. And H is the height. But I'm going to put height in quotation marks here, measured in meters. Why quotation marks? Because it's relative. The height above what? The height above whatever you want. Pick whatever spot you want to measure it relative to. Okay, measure the height of me on the cliff relative to the water if you want. Measure it relative to the top of the cliff. It doesn't matter. Measure it relative to whatever you want. You just got to specify what you're measuring it relative to. Let's try this example on 6.3, page 298. It says, figure 6.14 shows a toy car set up on a tabletop. We want to know the gravitational potential energy of the car, which has a mass of 0.0250 kilograms, relative to the floor. And then we want to find the change in potential energy of the car when it arrives at the bottom of the hill. So for question A, the gravitational potential energy relative to the floor. M, the mass of the toy car, is what? 0.025 kilograms. G is 9.81. What's H? What height do I use? There's two different heights here, right? 2.15 meters, 0.950 meters. Well, then you could even subtract the difference, right? 2.15 minus 0.95 would be this distance right here, from the top of the table to the top of the hill. Which one do I use? Why do I use the 2.15? You're right, by the way. Why do I use the 2.15? Right. If I'm trying to find the height relative to the ground, then let's use the 2.15. Okay, if I'm trying to find the height relative to the tabletop, then let's use whatever that height is. All right, let's figure that out now. Gives us a 0.527 joules. Okay, straightforward enough if you recognize which height you're supposed to use there. Question B says, what's the change in potential energy of the car when it arrives to the bottom of the hill? Well, let's find the potential energy at the bottom of the hill. This is the top of the hill. Let's do the bottom of the hill. What height do I use now? Didn't we say I could define my 0 point wherever I wanted? Could I make the bottom of the hill 0 potential energy? I could if I wanted to, but not in this question, because if we're trying to find the change in potential energy from the top to the bottom of the hill, we have to be consistent with whatever we define as our 0 point. Okay, in the first question, we defined the ground underneath the table as my 0 point. Everything was measured relative to that. I have to do the same thing for question B then. Okay, relative to the ground, the height at question B is 0.950 meters. Let's get that number. Okay, we should expect to get a smaller number here. 0.025 times 9.81 times 0.95 gives me 0.23298. That's not my final answer, though. How do I get my final answer, the change in gravitational potential energy when the car arrives at the bottom of the hill? Yep. Yeah, just subtract them. Just subtract them, right? So take that number subtract it from 0.52728. And we get, we'll say delta EP, the change in potential, as negative 0.294 joules. Why negative? Energy is a scalar, by the way. There's no direction associated with it. So what does that negative mean? Doesn't mean left or down, doesn't? Yeah, it means we lost energy. Okay, the final minus the initial, 0.2329, subtract 0.527. We've lost energy. The change in energy will be negative, right? All right, let's take a look at these 3 practice problems. That's where we're going to leave it off for today, and that's what I want you to finish up for homework for tomorrow. Remember, you got a quiz tomorrow. The quiz is one of these problems where we have one object, you're pulling on it 3 different directions here. What's the net force or what's the acceleration? And you have these 3 questions to do as well for homework, okay? Let's get a good head start on them now. There's about 10 minutes before the bell goes. Hey, maybe you even get them finished. If not, finish them up tonight and prep for that quiz tomorrow, okay? That's it.